Hi everybody, welcome back to class again. What we're starting today is looking into the actual beginning stages of the physical science class. In physical science is where we're studying the interactions of energy and the interactions of matter, basically chemistry and physics. To get the basic understandings of these and to be able to fully understand it, you need to understand measurements. And measurements is what we're going to be starting to look at today, and just how important a measurement is. So the first thing is, what is a measurement actually? Now, before we even get there, what I want you to know is on your notes, it's going to be a Google Doc this time, and I'm trying to make this change, and hopefully this goes a little bit better than Google Slides. But it is a Google Doc, but if you look on your Google Docs, you'll see up in the top, right above where I have this heading, it says reading dash CK12 1.24. That is a hyperlink that is going to take you to the readings for this section. I will also include this on Google Classroom as a separate link, but that will be a hyperlink that is available for you to click on, and it should take you straight to that website. If for some reason it wouldn't, let me know so that I can make that change on my end. But moving into this now, you are also going to see everywhere that there is red, I highlighted the words that you need to fix or fill in your notes in red, and it should be a red line in your notes. So, with measurements, what is a measurement? And you've probably taken measurements throughout your whole lives: weight, a length, how much liquid you're going to put into a drink. All of those are measurements, but you never thought about what an actual measurement is. What makes a measurement? And a measurement has two parts: a numerical value and a unit. And you need to have both of these. Both of these are vitally important to do, or to have, I should say. For example, if you told someone you bench pressed 400 and you were proud of it, they would probably understand that you mean you're bench pressing 400 pounds. But they wouldn't actually be sure. They're making an assumption that you're saying, if I bench press 400, they're going to say 400 pounds. But what you didn't give them is a unit. Was it pounds, grams, or like SpongeBob over here to the side, is it teddy bears? You need to have both a numerical value, a number, and a unit for something to be a good measurement. For example, down on this ruler, you have a pencil and it comes down right across here. And it comes up a little short there. I'm trying to draw it. Let's see if I can get it this time. There. Now the pencil comes up a little short, but we're going to call it right now 4 inches. 4 inches. It's probably actually somewhere around 4 inches and 15/16. But we're not going to get technical right now for math class. We're just looking at the unit or the actual measurement. With your measurements, you have your numerical value, or just simply saying a number, and you also have the unit. And the unit will change depending on what you're measuring. Some units are just for volumes, like liquids. Some are for masses. Some are for lengths, distances. And there's multiple units depending on what system you're using. So measurements are going to be very, very important. Now here's an idea of why about units being standard. And standard, I mean the same. They're constant. They're consistent. Here at the school, I'm asking students to measure the length and width of their desktops, the black tables. And if you're at home, I want you to measure the length and width of your kitchen table or coffee table or some table at your house. But you are not allowed to use any type of measuring device. No cell phones, ruler, tape measures, meter sticks, anything. No actual measuring devices. What you'll find, and let's just do a drawing here, is if we have a table, I've seen students measure so many different ways and they get really creative. And they'll start taking their foot, let's say their shoe, and they start measuring increments using their shoes. And they line them up and they go down the table. And in this case, they would say, well, we've got about 2 3/4, or sorry, 5 3/4. We have 5 3/4 here. 5 3/4 what? And they'll say 5 3/4 feet. So let's just say 5 3/4 feet. I'm going to say 5.75 feet because in science we're always going to use the decimals, but 5.75 feet. If a student used their shoe though, are you absolutely sure? Are you sure that that is perfectly dead on a foot? And the answer is no. And that becomes very important in the world of measurements, because if one shoe, if it says it's a size 12 shoe and the measurement's off a little bit, it doesn't seem like much while it's on your foot. And let's say we have one line here that is a foot, we call it a size 12 shoe, and another one here that is just slightly longer, and it's a size 12 shoe. Well, again, it's not much of a difference, but if you start lining these up end to end, and I'm going to try to draw these as close together as possible in size, all of a sudden by the second one, that distance or the difference between the two distances becomes a little greater. It becomes a little more noticeable. By the third one, it's even more noticeable. Now, these aren't perfectly lined up, and I do understand that. But you're getting the idea of where they'll become a little different and a little different over time. And if you did this over long distances, this could really screw someone up. And that's why measurements must be standard. And that's why it's so important for a measurement to be standard. And one of the biggest mess ups, the biggest flukes that have happened is back when NASA actually crashed a Mars rover into Mars. They crashed a couple $1 million satellite. They crashed it right into Mars. And NASA is supposed to be the real smart geniuses of the world. But what happened was, one group, NASA had this built in 2 different places, and parts are coming in, and you have people doing the calculations for the vectors to coming in, the angles, the speeds, the distances to the planet. And you had one group doing measurements in English and another one doing it in metric. And if you look up differences in sizes between these two, it doesn't seem like much, but it's a lot over long distances and long periods of time. And because of this, and it wasn't standard, because here in America, we still use the English system instead of the metric system. Because of that, the satellite crashed because somebody didn't do the right conversions and because the measurements weren't standard. Measurements must be standard. So now we're moving into measurements now, and in this science class and in the scientific community, you're going to use these things called SI units. SI units. And you also see on your notes that there is a hyperlink on this heading here that's going to take you to a pretty interesting article talking about how the masses, the kilogram, is measured and how it's kept safe here, like how we're measuring the standard and how the mass, the measurement for a kilogram is changing now that we have more sophisticated technology. But in science, we're going to use the SI units. And it comes from the French word Système International des Unités. And if I said that incorrectly and you speak French, please let me know. But this comes from, and it's more commonly known as the metric system. And again, there's a little link here. If you click on Système International des Unités, it'll take you to another quick little article from the History Channel talking about the SI units. But they're more commonly known to you as the metric system. But the reason they come from the French word is these measurements started to come about after the French Revolution, back in the late 18th century. And after the French Revolution, people wanted change. And the reason they wanted change is there were so many different ways to measure things in France alone. when you look at the one article from the History Channel, if you look at the article, there were nearly 400 different ways to measure area. The area of land in France. 400 different ways instead of just doing length times width times height and figuring it out. There were 400 different ways to measure it. That's way too many. So what they wanted to do, they wanted to standardize. They wanted to make everything the same. And after the French Revolution, this is what came about. And there was a whole bunch of reasons to it, but it helped. And later on, in 1960, it became the official measuring system of the scientific community at the 11th General Conference of Weights and Measures. And that would be an entire conference based on that. Going over just different masses and deciding in conferences that last for days. I couldn't imagine how exciting that conference would have been. To sit there and learn about a mass or talk about a mass and argue about that for days on days. I'm glad somebody else had to do it. How about that? But that was officially adopted by the scientific community at that conference in 1960. And then in 1975, the U.S. attempted to adopt it with the Metric Conversion Act of 1975. But it didn't officially happen. There's too much pushback. And it's unfortunate because the rest of the world uses us. There are, I believe, 195 countries in the world. 192 of them use the metric system as their main measuring system. Only 3 do not. And one of the most developed countries in the world, the United States, us, we do not use the metric system as our main form of measurement. But the rest of the world will. And I think it's Myanmar is in the process of transferring over. So there's about to only be 2. So that would be 193 countries would use the metric system. I think we need to get on board with this, and it'll make life a little bit easier. And the reason it's going to make life easier is because the scientific community and the medical communities primarily use the metric system. When you go to the doctors, if you ever sitting around the doctors, you hear somebody talk about cc's. They're talking about cubic centimeters. They're talking about metric measurements. They're not asking ounces. They're not asking fluid ounces. They're asking metric. When you go to college for any type of science, they don't use English units anywhere. They use the metric system. So it would be helpful if here in the United States, we could transfer. We use it. You see it still. If you go buy a bottle of soda, how do you buy it? 2-liter bottle. You don't buy it by the gallon. But you'll buy milk by the gallon, but you'll buy a bottle of soda by the liter. It doesn't make sense whenever you think about it that way, and other people around the world get confused with us because we make it so hard. Now, with going on here with the SI system, there are 7 base units, and you must know these. You must know these, all 7 of them. You must know that the base quantity length is measured using the meter. Mass, kilogram, time, second, electric current, ampere. You ever hear of an amp? That's where it comes from. Temperature is Kelvin, and we'll learn more about that later this year when we get into the energy section. Amount of substance is with chemistry called the mole, and luminous intensity is candela. I always remember this by thinking if you look on spotlights, it says candle power. And that looks like real close to the word candle to me. Over here, you see all the different symbols. So meter is abbreviated lowercase m, kilogram is kg, seconds is lowercase s, so on and so forth. Now, I have had people ask me, why do we not use the gram as the base unit for mass? Well, whenever you think about that, that would be down here. The kilogram is the base unit because, 1, the gram was too small to reliably measure when these units were created. When they first came together to figure out what was going to happen with the SI units, a gram is really, really small. And I'll have pictures to show you just how small a gram is. It's really, really tiny. A kilogram is the unit that most commonly is used in derived units is the second reason. And what I mean by derived units are over here. Derived units that are made with combinations of the base units. They're not a base unit. They're made from different combinations. And when you look, we can see over here, kilogram with meter and seconds. That's 3 base units. You have a Newton meter, which, again, a Newton is up here. So it's still 3 different units. Kilograms, meter cubed. Meters per second. Meters in newtons. Meters per second. There's 2. Meters per second. Meters per second squared. You don't see any of those here. But because you can combine them in different ways, you can get derived units. And you don't see grams anywhere over here. Kilograms is the most commonly used mass measurement, so that's just what stays, because then all these equations and all these calculations would have to be changed if we changed the kilogram here to gram. So 7 base units and then derived units. Be able to identify or differentiate between the two. And the best way to do that is memorize what the base units are and then look at a derived unit and say that's not one of the 7 base. So it can't be that. It must be a derived unit. Or if there's more than one of the 7 base units. Now prefixes. SI units have prefixes. The same way that you use a prefix in English class. A prefix is going to go before the word. So all of these prefixes will go before a measurement, the word for a measurement. So, for example, you have meter. You could have I'm going to change colors here. Let's go green. You could have a kilometer. You could have a centimeter. You could have a gigameter. You could have a millimeter. And all of those, it's telling you a different amount. The word meter is your root word, your base word. And then kilo is your prefix. Centi is your prefix. Milli is your prefix. Giga is your prefix. And each one of those prefixes is telling you a different amount. If you have a kilo of anything, it might not be able to understand so much with the exponents, but a kilo means 1,000. This is what I want you to remember here. So a kilo would mean 1,000. A hecto would mean 100. Deca means 10. So if you have hectobuses, you have 100 buses. If you have a kilogram, you have 1,000 grams. You can add that prefix to anything and it just tells you the amount. And then you go down the other way where deci means 0.01 or 1/100th. Sorry, 10th, 1/10th. So then you have centi, 1/100th, 1/1000th for milli. And it keeps on going down through the list. Those are what the prefixes do. They go before the word. And they always change by multiples of 10. Either by multiplying or dividing by some multiple of 10, you change your prefix. Now, in this class, the most common ones that you are going to see, and the ones that you must, with 100%, without a shadow of a doubt, remember, are milli, centi, and kilo. You are going to see those for the rest of this year. Right now, though, in this class, I'm not going to require you to learn more than from mega to micro. Mega to micro, to memorize. Those ones you're going to have memorized, and those will show up on a quiz. Those are the ones that you're going to have to learn there. And make sure you use the appropriate prefix to match what is being measured. It says here you don't want to be measuring a football field in micrometers. That's really small. If you had a millimeter is about the width of a credit card, you don't want to be measuring the width of a room using just something the thickness of a credit card. Now you're probably going to be going to the meter. Use the proper prefix or the proper unit of measurement. Thank you, everybody. I hope you have a wonderful day. If you have any questions about this material, please feel free to email me. Please make sure to look at the reading, the CK12 reading at the very beginning. That is the hyperlink that I want you to really focus on. The other two hyperlinks are for fun and to give you some more information and to give you some interesting information about the SI units. Thank you, everybody. Have a wonderful day. Bye-bye.